Hey guys, so today I'm going to talk about indexing blockchain data, in particular how the graphs indexing system work underneath the hood. So a couple of topics I'm going to cover today is Firehose and Substreams, which are the latest development in terms of the indexing engine that they have been working on. So if you've ever tried to get blockchain data, if you ever tried to work with blockchain data, you probably noticed that it's not easy. It's kind of like a pain in the ass. And when we first entered the space earlier this year, we decided, hey, we're not going to get all the raw data. We're not going to run all the nodes ourselves. Instead, we'll use the graph as our data infrastructure. And in particular, we joined the graph earlier this year as one of the core subgraph developers in order to contribute to this open ecosystem. And just a quick overview of the graph's indexing architecture in case you're not familiar. So this is I guess a diagram of how different parts fit together. And the graph is a decentralized data indexing infrastructure that allows anyone to become an indexer. So you can run your own graph node and index data to build subgraphs. So the way it works is that it will it will take raw blockchain data and will process them, extract the raw data, and then feed into different mini data pipelines that are called subgraphs. And the subgraphs are essentially logic that will take the raw blockchain data, will transform, aggregate them, and will turn them into higher level metrics. We'll put it in the store here that's powered by a Postgres database, and it will open up the data to be accessed by anyone using a GraphQL API that you can see here. So it makes the access to blockchain data much easier. And if you went to the talk that Eva gave earlier, you probably know that there's hundreds of protocols that have built thousands and thousands of subgraphs over the years. So it powers a lot of Web3 data infrastructure, and that's why we've been working with them closely. Now, so although it's great, it has some problems. And the biggest problem is the indexing time, which can be very slow, especially if you're working on high throughput blockchains. For example, Binance Smart Chain, Phantom, Polygon. Indexing a subgraph on those chains could often take days, if not weeks. And that, in turn, will lead to long development cycles. So if you're trying to debug something, you will need to deploy that subgraph. It will take a couple hours to index, sometimes even longer. And then you see the output, whatever the log statement that you put in there. So you have to do that process over and over again to debug the issue that you're seeing in those subgraphs. And another issue is that subgraphs are not composable, meaning that you cannot build a subgraph on top of another one. You cannot take the input, well, you cannot take the output of one subgraph and use it as the input of another one. So the graph have been working very hard in the past couple years to solve some of these problems. In particular, there's a solution called Firehose that has been developed by one of the core graph developers called Streaming Fast. And what Firehose does is that it extracts all of the raw blockchain data from the blockchain clients into flat files, for example, the protobuf files that you can easily access. So it essentially decouples the reads that people make to the JSON RPC nodes from the writes. It also extracts the the block data in such a way that it has a lot more data than what's available in the JSON RPC nodes. It's very exhaustive. It includes a lot of the state changes, the deltas before and after, such that once a block has been processed by the Firehose, you never need to go back to the JSON RPC node again to get data. It could serve as the single source of truth. So another way to think about it is in the traditional Web 2 data pipeline, you have the ETL stages, right? Extract, transform, load. And Firehose is basically serving the job of the extraction layer here, extract all of the data from the Ethereum clients. And what this enables is that with all this data now as flat files, you can much easily distribute them over many different places. It's much easier to duplicate them. It enables parallel computing, which I'm going to talk about a little bit later. And the data is also being exposed in a streaming first manner. So you don't have to pull the data every 15 seconds or so. All the data will be pushed to you. And with this this kind of Firehose way of dumping all the data onto the disk, it will significantly reduce the reliance on archival nodes, which tend to be a pain to work with. Yeah. So this is really great. Next, I'm going to talk about substreams. You can think of substreams as the transform layer of the ETL pipeline. So it will take the raw data extracted by Firehose. It will process them in a way. It's kind of similar to subgraphs, but it's much more modular. And then it will put the resulting data that's been processed into a graph node that people can access using GraphQL. So if you've worked with subgraphs before, you probably know that subgraphs is a pretty monolithic kind of architecture in that for every subgraph you build, it does everything end to end. So you're responsible for doing everything from getting the events, processing them, aggregating them on the pool level, protocol level basis, and then exposing them at the very end. So it's end to end. It covers the entire vertical. And if you wanted to, for example, take some data from Curve and use in your Uniswap subgraph, you cannot do that without having to copy paste that code over or just rewrite that code. Substreams, on the other hand, solves that problem in that it makes the data pipeline very modular and very composable that you can reuse in like different places. So, for example, if you wanted to take out some event data from Uniswap, you can write a substream module that will take all the blocks as inputs, you parse them, you pull them out, store them as individual events, swaps, for example. And then later on, you can use those swaps in other substream modules. Though it's much like you know how DeFi is a Lego, money Lego block. Here is the data Lego block that you can do with substreams. So because of this, they are highly composable. It allows for parallel execution. So all of the substreams modules that you have built, they could be parsed by the substream compute engine, and then it will generate a compute graph, a dependency graph, in which it will be able to distribute that across many different nodes and execute them in parallel. So it will speed up the indexing time by orders of magnitude. And because of that, it will also allow developers to develop in a much shorter cycle. So another benefit of substreams is it does a lot of caching. it's caching every layer of the modules that you work with. So I'm going to show you a little bit later, but you see that for every substream module, there's going to be an input and output defined. And every time a substream processes a set of data for one particular purpose, right, it will cache all of the data such that if you ever need the output of that module again, it will not be recomputed. You can just pull that data and reuse it right away. And just as a cherry on top, they are written as Rust instead of assembly script, meaning that you get all the kind of the safety of that language as well as a ton of libraries that have been written by other people, so you don't have to reinvent the wheel every time. Yeah. So I wanted to show you an example of a substream, just like a subgraph, where you use a subgraph manifest to define how things are connected. You do the same thing with substreams. Specifically here, I'm showing 4 different modules. Some of them are maps, some of them are stores. The maps are stateless compute functions that will take a certain kind of input, will do a bunch of stuff to it, and produce some kind of output. Whereas for the stores, they will just take some data and will save them in memory or in cache. And the nice way about deconstructing the data pipeline in different modules is that it allows the compute engine to be able to massively parallelize all the code. So if you're familiar with either MapReduce or like BigQuery, some of the popular Web 2 compute engines, it works in a very similar way. Yeah, so this is an example of what a map looks like, a map module. So you can see in the top here that it takes a block as an input, and it gives a pair-created event as an output. So the code is very simple. There's a for loop. It goes through all the event logs in that block. It will check the ones that are emitted by the Uniswap factory, and will turn that parameters into a data structure that we defined, and we'll pass them on to other modules. And it's completely stateless, and it allows for all of the data to be cached and reused later on. So this is an example code for the store. It's also very simple. All it does is it takes the events that are outputted from the map module that I showed earlier, and it will save them into memory, well, on the disk. So this is an example of the compute graph generated by the Substream compute engine. As you can see, it's divided into many different stages. There's all this dependency tree that you can look at, that you can use to visualize. And it will also help you to understand as well as to debug the data pipeline much easier. So lastly, I wanted to talk a little bit more about the standardization work that we've been doing. If you've seen our subgraph, you probably know that one of the key contributions from Messari as the core subgraph developer is that we've introduced standardization on a lot of the subgraphs that we've been building. So that allows data consumers to very easily consume the data because they don't have to know all of the idiosyncrasies of individual protocols. So for all of the protocols in the same protocol category, you can use the same query. They'll all follow the same structure. So that's really nice, but it does have some limitation in that it's a very kind of it doesn't give you a lot of granular control over the data that you can get. Whereas for substreams, we can also have a standardization on top of that. But not only you can have standardization on the protocol types, we can standardize basically at each and every layer of the data pipeline. So we can define a standard for what swaps will look like. So it doesn't matter where whether you're getting a swap from Uniswap, from Curve, Balancer, Bancor. We can make it in such a way that they all adopt to a same standard, and they could be consumed by different substreams built later on. And yeah, so there's a lot more about Firehose and about substreams that I'm not able to cover today due to the time limitation. But if you're interested and you want to learn more, be sure to check out the official documentation on Streaming Fast website. And if you're interested in the subgraph work or the substream work that we have been doing, you can also check them out on our GitHub. So all of the work that we are doing are open source, and we encourage people to come and contribute. And lastly, all of the subgraphs we're building, we're powering some of the products that we have announced yesterday using those data, in particular protocol metrics that you can find over here, as well as data apps. And yeah, that's everything I have.